All right, it says we're recording, and we're going to start on chapter 4 now. And we're going to talk about scatterplots and correlation. All right. So the idea here is a scatterplot. This is going to be really the bummer. I normally teach this one in Excel, but anyway, we'll do our best. It's a visual representation to show the relationship between two variables. And the idea is to try to put the explanatory variable on the x-axis. And so my question is, let me open up a new page here. Okay, so the idea here is that we're going to create a graph. Okay, and it has two variables on here. We've got an x and a y. Okay, so this is going to be your x variable. This is going to be your y variable. And we try to make this the explanatory variable. And then your y is going to be your response variable. Okay. And so the idea here is so you're just going to plot the x variable and the y variable. And I'm just putting little circles here, but these are just dots. Okay. Sorry, some dots are bigger than others. They're all supposed to be the same size. Okay, so we're going to plot a bunch of stuff. Okay. So the idea here is, maybe it'll be easier to find some stuff online here. Let me scatter plot. Okay, so oh, these are good. Wikipedia, you gotta love Wikipedia. Okay, so the idea here is, as we're looking at these, so this is a scatter plot. You've got your explanatory variable down here, which apparently is process input. And then you've got your quality characteristics, which is whatever that is, okay? So you're gonna have a scale on there. And the idea here is you can see that as we plot the x variable down here, y variable here, this is kind of has a downward trend. This would be an example of temperature and sales. Does temperature affect how much sales you get? You know, maybe on hot days, you're going to sell more cool drinks or something like that. And so you can see this one has an upward trend. You can see that in this case, when the dots are really close together, we'd call that a strong positive relationship. When the dots are farther apart, we would call this a kind of a moderate. You can still see it's kind of a downward trend. You can see that there's really, you can't see it upward or downward. So this is what we would call a null plot, which means there's no relationship going on. And in this case, you can see that this one's kind of a parabola, looking at sort of a thing. And so this would be a nonlinear correlation. So as we're looking at these are kind of the four sort of things. And let's see here, we got some more. So here's another scatter plot, simulation time versus surface temperature. And so this one, you'd probably say this one kind of has a weak negative correlation. This would be an example of a strong positive correlation. You get your independent, in fact, this is a good thing here. Get your independent variable down here, your dependent variable down there. Okay, so we would generally call the independent variable the explanatory variable and the dependent variable the response variable. So that's another way to talk about those. Also notice here we've got this value that looks like it's really out of line with all the other ones. So we might look at that and say that seems to be a little bit of an outlier. Outliers can be just strange numbers. Maybe that's a typo, or maybe it really is there. When you have an outlier, generally what happens is your trend line, the trend line that we're trying to draw here, it's probably going to change and move towards that point somehow. And so, so a lot of times we want to look at those outliers, especially if it's a typo. You might want to remove it. Let's see. So this one. So as you guys look at this one, how would you describe this scatter plot here? Would it be a strong or weak?
Strong linear, positive linear.
Okay, anybody else? Do you agree with that? See, I would actually say this one's probably a null plot because you can't, I mean, you could draw a negative line here, a positive line here. There's not really a pattern in this case. So this would be a good example of a null plot. How about this one?
Negative.
Yeah, this is definitely a negative correlation. Looks like you might have a few outliers in this, but the general pattern is in the negative direction. Okay. How about this one?
There's kind of a delay. It's still showing the negative one that you had.
Oh, really? Maybe I'll stop sharing and then I'll share again. See if that helps. How about now? Can you see this?
Just seeing Easton.
Really?
There it goes. That one looks like a positive linear.
Okay. Yeah. So positive, this one would probably be either moderate or weak. You can see these are really spread out a lot more than if we go back to the negative. This is a pretty strong correlation. Although you do have, this is the red one that I showed previously. These are a lot closer together dots with a couple of possible outliers there. Let me see if I can find. Okay, here's one. This one's kind of interesting. So this one has green dots on it. Do you see this one kind of has a curve to it? It's almost, you could almost say this one's an S curve. Does that make sense? I've got education on the bottom and females and thousands on the y-axis. I'm hoping that you got my screen's catching up.
Yeah.
Okay. So this one, I would say, this one's more of a non-linear because this one looks like more of a curve. I mean, you could draw a straight line on here, but this one's a little bit more curvy. I will show you this because Wikipedia does have some good graphs here. And so oh, this isn't the right one. Okay, sorry, wrote it backwards. Okay, but the idea here is, this is a really good one. Okay, this is one of my favorites to draw. Okay, all right. Now, so scatter plots are related to a correlation coefficient. Now, a correlation coefficient always is between the values of +1 and -1. So in this case, in this middle line, you can see that it's not necessarily the slope. All of these are perfectly correlated. If you took a variable and you on the x-axis and then you put the same variable on the y-axis, you would get a straight line. So these three on the left here are positively correlated. They're all perfectly correlated, 1 versus 1. And on the left side, -1, these are all in the negative direction. So these are positively correlated because it goes from low to high, low to high, low to high. And then these go from high to low, high to low, high to low. These are all negatively correlated. So the idea with the correlation coefficient is we're trying to see how close the dots are together. So once again, perfectly correlated in the positive direction, perfectly correlated in the negative direction. And then the idea here is, as we're doing this, we're trying to see how close the dots are together. So this one here is a correlation coefficient of 0.8. We would call this a strong correlation in the positive direction. This would be a -0.8, strong correlation in the negative direction. 0.4, we'd call this one more moderate. This is -0.4 in the negative direction. And then this here is a null plot. There's no correlation. There's no pattern to these dots here, okay? And so the idea here is the correlation coefficient, you should always, whenever you're calculating the correlation coefficient, you should always be looking at the scatter plot. And I will show you how to do this in just a minute. So the idea here is we've got a formula for the correlation coefficient, which is this formula right here. Okay, so R equals 1 over n1 minus, R equals 1 over n minus 1 times the sum, and then you can think of these as z-scores. This is your x minus x bar, or the x minus the mean over the standard deviation of x, and y minus y bar over the standard deviation of y. So essentially what these are is you're taking the z-scores for the x, the z-scores for the y, you're going to multiply them together, you're going to add them up, and then you're going to essentially divide by 1, n minus 1, excuse me. And now I'll show you an example in just a minute. But the idea here is this formula for the correlation coefficient, we always use the letter R to represent the correlation coefficient. So R always assumes that we're looking at a straight line correlation, okay? Now, the problem is, let's look at this bottom line here. Okay, so if we're using this equation here, R equals this, to calculate it, all of these on this bottom line have a correlation coefficient of 0, okay? Now, if you have a correlation coefficient of 0 and your scatter plot looks like a null plot, like this one does here, then you can say, yes, there's no correlation going on. But on this bottom line, all of these have a correlation coefficient of 0, but you can see there's a pattern. So in this first case here on the left, this looks like kind of a big W. This is what we would call a nonlinear correlation. So whenever you're calculating the correlation coefficient, you should first look at the scatter plot to make sure that it really is a straight line, the top line. Because if you look here, it is not appropriate to do a correlation coefficient, because this is what we would call a nonlinear correlation. Now these next two, these are kind of weird things. You wouldn't see that in real life. You would see this in real life, this kind of W-looking pattern. You would also see something like this. This is kind of a parabola. This would be a nonlinear correlation. I've never seen anything like this in nature, but this would be two nonlinear correlations. This would tend to make me think that I've got two different populations of some sort. I've never seen anything like this in nature, but you can see once again, this would be a nonlinear correlation. And so in this case, it would be inappropriate to calculate the correlation coefficient. And these look like four different null plots. Once again, so when you're calculating your correlation coefficient, it's important that you're looking at your scatter plot first to make sure that, that calculating the correlation coefficient is a good thing to do. So the idea here is you're gonna put the maybe I'll put this on here, the explanatory or the independent variable on the x-axis and the response or the dependent variable on the y-axis, okay? And so as you look at this here, would you say that this is strong, moderate, weak, or no correlation? And is it positive, negative, or non-linear? Okay, so Wes has been answering a lot of questions, so I don't want him to answer this one. But would you guys say this is strong, moderate, weak, no, and positive, negative, or nonlinear correlation, what I've drawn on here so far?
I think it's weak.
Weak, okay. Anybody else?
Well, I would say probably moderate and positive.
Yeah, I'd probably go with that too. I'd probably go with, yeah, moderate. I would agree with you. That was Easton, right? Moderate and positive. Okay. Sometimes it can be hard to check these. You could maybe argue weak, but I would probably go with moderate on this, and definitely positive. Okay. So we will give you a bunch of scatter plots. Kind of, if you want to talk about this, strong, and I'm going to talk, is going to be the pot. So if we talk about the absolute value, so if the absolute value of R is greater than 0.7, we're going to call that strong. Moderate, in this case, we're going to use the absolute value of R between 0.3 to 0.7. And your weak, we're going to say the absolute value of R is less than 0.3, and no correlation would be close to the absolute value. Absolute value of R is close to 0. So it's funny because I always give students these rules, and then I break them. I'll break them on Monday. But so when we're looking at this, those are kind of so long as you're looking at a scatter plot, these are kind of some good rules that we'll do. So greater than 0.7 strong, between 0.3 to 0.7 is moderate, less than 0.3 is weak, and close to 0 is going to be no correlation. And yes, this is in the positive direction rather than the negative, and it looks pretty linear. Okay, does that make sense? All right. Okay, so these, yeah, essentially what we're looking at, these are kind of your z-scores for the x variable and for the y variable. And so, so these are some good steps that I would like to do. Normally, I make people do these in Excel because it's actually easier to do in Excel, and I will do some examples in here. And in fact, we haven't done this for a in fact, I don't think we've ever done this in this class. This is going to be kind of fun because we've got a small class here. So what I'd like to do is I would like to see, I'm going to open this up, and in fact, I'm going to copy this here, and we're going to calculate the correlation coefficient. So what I'd like to do is, I want to see, or let me first ask you this. Do you guys think that your shoe size and your height might be correlated? Do you think there would be a reason to believe that those would be correlated?
Yes.
Okay. So here's what we're going to do. Now, the question is, okay, as we're drawing this, okay, let me go back to here for the question. And some of these can be a little bit hard. So the question is your shoe size the explanatory or independent variable, or is your shoe size the response variable or the dependent variable? So think of it this way. Does your shoe size explain how tall you are, or does how tall you are explain your shoe size? This one's always a tough one, because you could actually argue this both ways. But let me do another one here that's a little bit easier, okay? Let's say that I'm trying to decide this. And that's why I'm not super strict on the explanatory, the independent variable. Let's talk about two variables here. A person's weight and a person's height, okay? First of all, do you think a person's weight and a person's height might be correlated?
Yes.
Yeah. So would you expect it to be, so we would say yes, okay? Now, the question is, would it be positively correlated or negatively correlated?
Positively?
Yeah, probably positively. You would think, okay, you would think that as people get, well, and we haven't decided which one's the independent or dependent variable yet, but you would think that as people get taller, their weight would probably go up, right? Okay. So now the question is, oh, actually, let me do another one. This one's going to be another tough one here. How about instead of doing weight and height, what if I did weight and, I'm going to delete this variable, and I'm going to say time exercising. Okay. So we're ignoring height for a minute here. Would you say that weight and time spent exercising would be correlated?
Yes.
Yes. Okay, now let's think about this. Okay. Would it be positive or negative? So let's think about this for a minute. For people who exercise more, would they have a lower weight or a higher weight? Than people who don't exercise, as a general rule.
Probably negative. Yeah,
this would be an example of probably a negative correlation. So we would expect probably a negative correlation. These dots are so big, I apologize. It's hard to draw on here, but okay. Now the question is, so we would expect a negative correlation. Now, as we're labeling our axes, does your time spent exercising, does that explain your weight, or does your weight explain your time spent exercising?
I would think it's the time exercising is explaining the weight.
Right. And so this would be an example in this case. So your time spent exercising would be your explanatory or your independent variable. And a person's weight would be the dependent variable, because a person's weight would depend on how much time they spend exercising. Now, as we go back to the shoe size and the height, okay, we would expect them to probably be positively correlated. But does your shoe size explain your height, or does your height explain your shoe size? That's a little bit harder to nail down which one's the explanatory. It's kind of a, short people are going to have smaller feet, tall people are going to have larger feet. Does your shoe size explain your height, or does your height explain your shoe size? You could argue that either way. In either case, you could. So this is one where it's a little bit harder to say. So I'm going to let you, and so I'm not super picky on some of these. This one here on the right with the weight and the time exercising, this one's a little easier to see. Time spent exercising definitely explains a person's weight, or your weight depends on how much time you exercise. So that one's a little bit easier. But in the case of, say, somebody's shoe size and their height, that one might be a little tougher. So what I would like to do, especially because we only have, how many people do we have here? 1, 2, 3, 4, 5, 6, 7 people here, okay? So what I'd like to do is I'd like to ask everybody their shoe size and their height, and we're going to try to find out, first of all, is this strongly, moderately, or weakly correlated, or no correlation? In fact, before we do that, one more thing. I'm going to take 2 more variables here, and then we'll talk about this. Okay, so how about a person's test scores and their height? Would you expect those to be correlated?
No.
No. Okay. So in this case, we would say you would expect there would be no correlation. Okay. If I were to draw a quick scatter plot here, and I'm kind of ignoring the scales, but let's do this when you're doing this, you should never ignore the scales, but I'm going to ignore this just to get the concept here. So in this case, you would expect, so it really wouldn't matter if you put a person's height here and their test scores here. Okay. In this case, you would expect there would be no correlation. And so, that was a big dot. Didn't mean that to be a big dot. Oh, I hate this. Sorry, these dots are so big. But you would expect there would be no correlation. So you would probably expect a null plot. So this would be an example of what we'd say no correlation, and you would expect a null NULL plot. Okay, you'd expect there would be no correlation here. And this one should be an example of negative correlation, negative. This one probably looks pretty strong. This would be an example of positive, and I would say probably moderate. Let me do one more and then we'll do our thing here. This one's always a fun one to do because this one probably people don't think about. Okay, what if I had, okay, so the 2 variables that I want to talk about are your time spent studying and your test scores. Do you think those would be correlated? What do you think? Somebody besides Easton or Wes.
I think there would be a correlation.
You would think there would be a correlation. But you know what's really interesting about this? There is a correlation, but it's actually nonlinear. Now, if you were to think this, okay, you would probably think, so which one would be the explanatory or the independent variable?
Time studying?
Yeah, you would think that time studying would be the explanatory variable, and you would think that your test scores would be your dependent variable. And so this is another example of, yes, you should be able to do this. But the funny thing is, I've actually done this in my classes before. And one of the things that we found was that the graph looked something like this. Okay, it was really surprising. Now the question is, why would a graph look like that? Would be an example of a nonlinear thing.
The people that
Why
didn't
do you think
attend
that
the class
might be the
decided to
case?
crash, study real hard at the right before test.
Yeah, so this is one of those things. You would think that time spent studying would explain your test scores, and it doesn't do a very good job of it, to be honest. Because some people are really good at math and they don't spend any time studying and they get a great score. And some people spend a lot of time studying and still get a terrible score. And some people don't study at all, they get a terrible score. Well, that makes sense, okay? And so this is one of those strange things where this is where so you get a result that's a little bit surprising. It often looks as a nonlinear thing. And so the idea here is, yeah, they're related, and it does. And so if you get something like this, it doesn't mean, oh, well, it doesn't matter how much time I should study, but there are other factors involved that affect your score. And in fact, I used to do this all the time in my classes. We would actually do a survey, and it might be fun to do that again, but not this semester. But we would do a survey on time spent studying and your test scores. Of course, I would come up with the test scores, and then the students would see, wow, this is kind of one of those weird ones where it doesn't work the way you would expect. Okay. All right. So let's go back to our shoe size and our height. Okay. So what I would like to do here, Bridger, you're here. Does your microphone work, Bridger? Bridger, can you please send me an email and let me know why, if there's something wrong with your microphone? I'd really like you to participate, but let's go with Allie. Allie, do you mind telling me your shoe size and your height?
So I'm 5'6" and I'm at 8.5.
8.5 shoe size and 5'6", so that's going to be 66 inches tall. I'm going to convert you to inches. It'll be easier to do. Okay, Bridger, can you answer? Tell you what, Bridger, if you can hear me and you just can't talk, text. You should be able to chat and type it in there. But I'm going to go to Easton next. Easton, what's your shoe size and your height?
Shoe size is 9. Height is 5'10".
5'10", which would be 70 inches tall. Okay. Janie, sorry, I always want to say Janae. Janie, can you tell me your shoe size and your height?
9.5, and I'm
9.5 shoe size. 5'7.5". So
Yeah,
5'7",
is very
67.5 inches tall. Say it again.
Oh, I was just saying the half is very important.
Oh, okay. All right, so that was Janie. Seth, can you tell me your shoe size and your height?
Yeah, 12.
Okay.
6'2".
6'2" would be 74 inches tall. Okay, now, Wes, can you tell me your shoe size and your height?
14, 75 inches.
14, you're a Bigfoot, man. 75 inches, okay? How about Yami?
I'm a size 9 and 5'6".
5'6" would be 66 inches. And then I don't think we got anything from Bridger. So that means Bridger cannot hear us. Bridger, you need to hear, hopefully. Okay. All right. So 6 is a little bit of a small sample size, right? Okay. Now, because I want to save a little bit of time, I'm going to use, I will tell you that Excel has a nice thing here. Now, let me ask, but before we do that, which one do you think should be the independent and the dependent variable, or the explanatory and the response variable?
I think height should be the explanatory variable and shoe size should be the response variable.
Okay, so here's what we're going to do. We're going to do it both ways. I'm going to leave shoe there because this is one of those that doesn't, it's kind of weird and it doesn't really matter. But I will just show you this because I want to spend more time on the formula. In fact, I should copy the formula. I wonder if this will copy. Oh, it copied very nicely. Okay, I will give you this formula for our test. Okay, I will not give you these steps to memorize. If you want to memorize them, you are more than welcome to. But anyway, so let's, first of all, we're going to look at our scatter plot. So if I insert a scatter plot, so this, oh, that's interesting. Okay. Now, a properly labeled thing should have labels on here. So this is going to be shoe size. And this is going to be height in inches. And maybe this is our math 1040 class. And so what do you guys think about this? This is a very small data set. If you were going to say, is it strong, moderate, weak, no correlation, and is it positive, negative, or no correlation? So I'm going to pick on Yami. What do you think?
I would say moderate and positive.
Moderate and positive, I would go with both of those probably. Now, I don't remember who it was, but the idea here is, here's what I'm going to do. I'm going to change this such that the height is the explanatory variable. And I want to show you what happens if we do this. So I'm going to insert a scatter plot here really quickly. Now notice here, can we put these side by side? Okay. What do you think? I should actually add my thing here. Okay, so now we've got height in inches, and you've got shoe size here. And this is also math 1040 class. Now, like I said, I want to spend more time figuring out the calculation or the correlation coefficient, but I'm hoping you guys can draw these. Now, would you guys agree, as Yami that we picked on? So Seth, let's pick on you this time. Would you agree that the graph on the left is moderate and positive? Are you there, Seth? We can't hear you. Did you walk away, Seth? How about Janie? What do you think? Do you agree with Yami that it's moderate and positive?
Yeah, I do.
Okay. So it doesn't really matter when you're looking at the correlation coefficient here. It doesn't really matter which one you put on the x-axis or the y-axis because we're going to end up multiplying them. You will notice here the slope is vastly different between these two. This one looks very steep slope. This one looks very shallow slope. The correlation coefficient doesn't care which one you use, which axis you use, but in both cases, if it's positive with this way, it'll also be positive here, but the slopes might be very different, okay? So anyway, I'm gonna go ahead and delete this one. It's gonna mess up my graph though, but that's all right. Okay, so actually maybe I'll do it, oops. Maybe I'll do it this way. Do you guys want to do it with height or shoe size as your explanatory variable? It doesn't matter mathematically when we look into this.
Height?
Okay. Okay. So we're going to decide the height. So that messed up that graph, but we'll just move it out of the way. All right. So okay. So as we're looking at this formula, so I will give you this formula here. Won't give you the steps. But the idea here is, in both cases, we need to find either the x bar or the y bar. So we need to find the mean of each, okay? So I'm going to find the mean of each of these, okay? So the mean height in our class is 69.75 inches. The mean shoe size is 10.33, okay? So we found the means. Now we need to find the standard deviations. Oh, I didn't think about this. Let me mention this on your calculators, okay? You can use your calculator. I made you guys figure out the standard deviation by hand on the last test, didn't I? Okay, now Excel has a nice thing here, standard deviation. Okay, this is going to be a sample. And so, generally, you're always going to use a sample standard deviation on these. So the standard deviation is almost 4 inches there. Standard deviation on the shoe size is 2.18. Now, I haven't looked at your calculators. Hopefully you have a calculator that will figure out your standard deviation. So Easton, just because I see your face, do you know what kind of a calculator you have?
Yes, I have a Texas Instrument.
What's the model number?
The TI 30X.
30X, okay. So if you don't know how to find the standard deviation with your calculator, here's what I'm going to recommend that you do. Go to YouTube and you're going to say, how do I find standard deviation on TI? You said it was a 30? Whatever, that's close enough. All of those should be the same. And you'll watch a 3-minute video and it will show you after the commercial how to find the standard deviation, okay? So I don't care whether you've got a Casio or a Texas Instruments, I can guarantee that almost every calculator has a video on YouTube on how to do that. So I don't want to spend a lot of time on this, but you will need to know how to do that to find the mean. In fact, your calculator, not only will it find the standard deviation for you, you'll be able to enter it in. If we watch this, you'll enter in all of these numbers in, and it will find your mean and your standard deviation, and it will probably find your correlation coefficient as well. Now, having said that, okay, on this test, I want to see all of the steps. Okay, so and in fact, well, I'll show you how to do it in Excel here in a minute, but okay, so the idea here is, so what I would like to see on your test is, I don't need to see all the calculations for your mean. I don't need to see all the calculations for your standard deviation, but I would like you to set it up something like this, okay? Now, essentially what we're doing here, okay, so we found the mean, we found the standard deviations. Now I need to find the standard scores for the X and Y. So in this case, I need to find the Z-score for the height. I need to find the Z-score for the shoe size, okay? And essentially, now here's where it's important, okay? When you're doing this, it's important that you use parentheses, okay? So I need to find the shoe size, the height Z-score. So I'm going to take the data, it's the mean, and I'm going to do a thing so that I can copy this formula here. Oops. And then, so your numerator needs to be in parentheses when you're entering this in your calculator. And I'm going to divide it by the standard deviation. Okay. So so the Z-score for the height is going to be these numbers here. Now I'm going to do the same thing with the shoe size. I'm going to take your shoe size, I'm going to subtract off the mean for the shoe size, and I'm going to divide by the standard deviation for the shoe size. Okay. So now I've just found the Z-scores for the height and the shoe size, okay? So I found the mean, I found the standard deviation, I found the standard scores, or the Z-scores, okay? Now I need to multiply the Z-scores together, so I'm going to multiply this, okay? So this is basically, you're going to have to be doing this with pencil and paper, but this is what I want to see, and I'll try to give you a nice short thing on here. If it was a computer, you could do these a little bit quicker, but so I'll give you a nice small data set. So I'm going to take your Z-score of your height and multiply it by your Z-score of your shoe size. Okay, so that's going to be 0.792. I'm going to copy these down. Okay, so I found my mean, I found my standard deviation, I've multiplied my Z-scores together. What does this weird looking E thing or sigma mean?
Find the sum.
Find the sum, okay? So this is the sum of the products, okay? And even Bill Gates knows that sigma means that. So I'm going to press that button. I'm going to find the sum. Now what does N represent?
Number of in your sample.
Number of my sample. So is my sample, is it 6 or 12? What do you guys think?
6.
It's 6. We've got 6 students in our class. We don't have 12, okay? So in this case, we're going to divide by 6 minus 1 is 5, okay? So if I take this number and if I divide by 5, that's going to give me a correlation coefficient of 0.91. Now, let's pull back our thing here. We were guessing that this was moderate and positive, right? Based on this value, what would you say your correlation coefficient is? It's definitely positive still, right?
Be strong.
But 0.91, we would say that is strong correlation. This would be positive and strong correlation, okay? Now, it's a little bit hard to tell when you have a small thing like this, just to eyeball it. But yeah, we would definitely call this strong correlation, okay? Does that make sense? Okay. Can you guys ace my test when you do this?
When is the test?
Next Friday.
The test is going to be a week from today.
Oh yeah, then I can ace it.
Okay. You got a week to learn this. Hopefully, actually, you really only have a weekend because we're going to give you the quiz. It'll be due Monday. Okay. All right. Let me see. Is there anything else that I've missed on here? Oh, now this is interesting. I need to show you these websites. Now, let me back up a second here. Occasionally, you may find something like we do with the time spent studying and the test scores. But even still, you'll find some other things. A lot of times when we're looking at this, we're looking to see if the response variable is dependent upon the explanatory variable. Now, the idea here is two items may be correlated, but may have nothing to do with each other, okay? So there's a really great website here, Tyler Regan's Spurious Correlations. And the interesting thing about this is a little bit different in that a lot of these are going to be nonlinear correlations. We're not going to do that, but this is interesting. It's taken a long time to load on my page for some reason. I wonder why. It usually loads very quickly. Okay, so this is U.S. spending on space, technology, and science, or science, space, and technology, and suicides by hanging, strangulation, and suffocation. So you can see, according to this, okay, the more money we spend on space, science, and technology, the more suicides we're going to have, right? So this would be, do you guys believe that those are really correlated with each other?
No.
No. How about this one here? Number of people who drowned by falling in a pool correlates with the films that Nicolas Cage appeared in. Because, you know, when you watch a Nicolas Cage film, it just makes you want to fall in the pool. Okay, how about this one? Yeah, maybe, if you hate Nicolas Cage. How about this one? Number of people who died becoming tangled in their bed sheets with per capita cheese consumption. I mean, clearly it looks like if you eat too much cheese, you're going to die becoming tangled in your bed sheets. Okay, look at this. We got a really strong correlation. Your correlation is almost 95%. That is a very strong correlation. Okay, and how about this one? Divorce rate in Maine and per capita consumption of margarine. Okay, eat more margarine and you won't get a divorce. Okay. We'll do one more here. The age of Miss America correlates very strongly, 0.87, with murders by steam, hot vapors, and hot objects. So apparently we want younger Miss Americas, and then there will be fewer murders, right? Okay. So the idea here is, anyway, there's a lot of them on here that are pretty funny, but you know, a lot of times when we're looking at correlation, you know, time spent exercising, that makes sense to correlate with your person's weight. Okay, so when we're looking at these variables, we need to find two things that make sense. Now, sometimes you may find something like time studying does not correlate well with your test scores. It doesn't correlate as you would anticipate. But the idea here is you should find two things that there is a reason to think that they're correlated. And so just because two things are correlated. There's another interesting website here. You can't trust what you read about nutrition. This is from 538.com. This is my favorite statistics website. Have I told you about 538.com before? This is my favorite statistics website in the whole world, I think. But it also talks about spurious correlations. Oh, this one, I guess you'll have to read this one. This one doesn't have any great graphs, but anyway, that can be kind of interesting thing there. I was thinking that one had some stuff on there. Okay, now here's another interesting thing. Lead might reduce crime. So this is really interesting. You know, lead, we now have unleaded gasoline. A lot of times they would put lead in paint, and apparently lead is really sweet. And so little kids would eat lead paint, and it would cause some serious, one of the big graph. Anyway, it would cause, it definitely affects your brain. Let's see if I can make this bigger. Oh, never mind. This is the as big as I'm going to get it here. I don't know why we have all these things here. Can I not close that? Anyway, so you can see the amount of lead increases. This is from 1937 to 1972. You can see that especially because lead was used a lot in gas as well as in paint, the crime rate inched up. And so then it was about the 1970s where they made a big push to get rid of lead in both paint and gasoline. And you can see that the crime rate seems to have dropped. And so so there seems to be a pretty good correlation with the amount of lead in the environment, especially paint and gasoline, and violent crimes. And so this actually does seem like there is a correlation, and a correlation that actually makes sense. I don't know if you guys are familiar with the Flint, Michigan water problems where they switched the water supply and gave all these people a bunch of lead in their water, and it's just a terrible situation. But it does appear not only is lead possibly related to violent crime, it's definitely correlated with affecting your thinking ability and test scores and things like that. And so we've got all these poor children in Flint, Michigan that have been exposed to lead, and it's probably going to affect them for generations, or for a generation. So anyway, so that's kind of interesting. I wish I could show you guys. We'll probably spend a little bit more time on another correlation coefficient problem here. Just want to finish up with a few other things, and then we'll go back to doing that. So this is from BYU, Idaho. I wonder if this is a better link than the one I showed you the first time. Just 1 second. Maybe this will give us a better. Oh, I think this is actually the graph. Mother Jones can be a little bit political, but this is one of the things. I swear they've changed their. I thought they would have a nice graph for me. Never mind. But at any rate, it does appear that there is a link between crime rates and amount of lead that people are using. Oh, this is a little bit different. Does lead make you dumber? And it appears the answer is yes. It does. It really affects the brain. Oh, this is that graph. Oh, that's interesting. Teen pregnancy. I never heard of that one. But this is the graph that they used before. It's a little bit bigger, so you can see a little bit better. But anyway, let me go back to here. Okay, so this is a table that they used to show it at BYU Idaho. They talk about the hot dog, the hamburger, and the banana shape. So they must have been hungry when they made these. But the idea here is when you're looking at a scatter plot, you kind of have a hot dog shape here. So that would be a good indicator of linear correlation. Your hamburger would be an indication that linear regression is not appropriate or correlation because there's no pattern going on here. And then you have your banana pattern. We didn't talk about the banana pattern, but this would be another example of a scatter plot that has a non-linear pattern. It says linear regression is appropriate. I would say no, it's actually not because it's curvy. And so it's probably better than a regular parabola. But yeah, if you see a curve in there, a natural curve, you'd probably be a little bit scared to trust both your, and we're going to talk about regression on Monday. Once you see that your scatter plot is linearly correlated, then the next step is regression, and we'll talk a little bit about that on Monday. So I will tell you this also on Netflix. I wonder if I have it here. Oh, you know what? Never mind, because I think they took it off Netflix. There used to be a thing on Freakonomics. Well, let me see if it's still on there. It wants me to sign in. Did I change my password? Oh, I think they made me change it. I don't remember what my password is. Anyway, maybe I'll try to post a link. Freakonomics. I would tell you this is really interesting, and you can watch it on. Okay, so this is really interesting. I'll try to post a link to this because I know you guys can't hear it if I'm doing this here. But the idea here is this is a really interesting video about. I'm going to jump to the graph here. This is only a minute and a half long, but at any rate. Okay, so this is the graph. Oh, back up. Okay. So this is an example of, in fact, it's called correlation and causality. What they found was back in the 30s, especially, polio was a horrible disease. And so one of the things that they found was for some reason in the summer months, polio spiked. And so they did an interesting correlation with ice cream. And they found out that, of course, in the summer months, people eat a lot of ice cream. And so there was a belief that maybe ice cream was causing polio. Have you ever heard that before? Yeah. So, but you can see, looking at these graphs, when we do ice cream sales and we do polio things here, it looks like that ice cream, and so there was a big belief, especially, oh, this is, I guess, in 1955, there was a belief that polio was caused by eating ice cream, and so it appeared that there was a strong correlation. They were trying to figure out, if there was something in ice cream that caused polio. So clearly ice cream doesn't cause polio. So this is another example of what we would call a non-linear correlation, but you can see that it sure looks like there might be something going on. So one of the problems when we look at correlation, and there's a common saying, correlation is not causality, okay? Ice cream does not cause correlation. So just because two variables are highly correlated, it does not mean that one causes the other, okay? And so the interesting thing about this is there's a lurking variable going on, okay? Now, does anybody know what causes polio? I'll just throw this out for anybody.
It's got a specific virus, doesn't it?
It's a virus, yes. And so the virus is in swimming pools and lakes, okay? And so what you have in this case is you have a lurking variable, and that is swimming pools and lakes, okay? And so the lurking variable, so it is funny because ice cream sales is kind of a proxy for polio infections. And you could actually use ice cream sales to predict how many polio infections you would have. But the lurking variable here is this kind of the summer months. So there is clearly something going on in the summer. But ice cream doesn't cause polio. It's swimming in infected lakes and ponds and swimming pools. And so that's another reason why we have chlorinated pools. It's really hard to chlorinate your lake, though. And so luckily we have a wonderful vaccine that prevents us from getting polio. But there was a line of belief that polio was caused by ice cream. And so this is a perfect example of correlation is not always causality. I will tell you there's another video here that I just want to mention really quickly from Freakonomics. In fact, tell you what, I'm going to post this video because it's only 1.5 minutes long. I will add that to my notes and I'll post my notes here. This one's a really interesting thing. Oh, well, maybe I'll save that one for the next lesson. I will. I'm going to save the abortion crime thing from the next one. Yeah, I'll save that for next time. So at any rate, that one has more to do with regression. So, okay, we've got about 15 minutes left. What I would like to do is I would like to do one more example because I am going to give you an example where I would like you to go through these steps here. And the problem is, tell you what we're going to do. We're going to see if random numbers are correlated. So I'm going to have an X, I'm going to have a Y. I'm going to pick on Allie. I want you to give me two numbers that I want you to come up with some random. So I want random number between what and what?
What and what? So like a random number?
I want you to pick up two random numbers. So
12 and 72, I don't know.
72, that's perfect. Okay. And let's see, I picked on Iami. Who haven't I picked on? Bridger never answers. Janie, can you give me two other random numbers?
I had to step away because I had to take a dog out, but 15 and 20.
Oh, that's kind of small. Go a little bigger.
40.
40, that's good. Okay, so these are just a bunch of random numbers here. And we're going to pretend this is a test question. Now, let me ask you guys a question here. Okay, so I just pasted this. Okay. Would you expect there to be any correlation between these two sets of numbers?
I expect it to be like the hamburger.
Yeah, you would. So you would expect a null plot, okay? Because now, if you guys,
Question, could it be
Yes, go ahead.
correlated just because Excel is going to use a similar programming to
that's
generate
such a
random
good
numbers?
question. So I have to tell you a funny story about Excel. There was a guy who used the Excel random number generator, and he found out that the numbers were not random. So there is a chance that these could be correlated. These could, because the numbers may not be random. Excel has since changed their format, and it's now much more random. But yes, there's a chance that it might not be random. So we would expect a null plot, and if I give you these numbers here, I would expect you to give me a proper scale for the x-axis and for the y-axis. But I want to spend more time on the thing here. I'm just going to draw this really quickly. That's kind of interesting. What do you think? Does that look like a null plot?
Yeah, it looks pretty straight across. I mean, there's no correlation up or down.
It actually looks a little bit curvy, don't you think?
Yeah, I guess it could be.
Yeah, it's a little bit curvy. So whether you would say, oh, this was a null plot, or you could say this is a curve, or rather than saying it's a curve, it's nonlinear. Okay. So I would probably say, so it should probably be a null plot. Maybe if we graph some more data, it would look more like a hamburger. But yeah, this one looks a little bit, this one definitely looks curvy on it. So I would call this a nonlinear plot. So, so the first question is, would it be a good idea to do linear correlation based on this scatter plot?
If it's nonlinear, probably not.
Probably not. We're going to do it anyway. All right, so here's what I would like to do. So I'm going to give you this formula on your test, okay? And so if you've taken good notes, hopefully you'll know what to do. And so I think we've got 6 people here that are listening. Bridger, are you here yet? Can you hear me? Okay. Send me an email, Bridger, and tell me why your microphone doesn't work. But here's what we're going to do. I'm going to have everybody, we'll start with Allie here. What's the first step that I should do based on this formula? Do you remember? Or you can look at your notes, but on your test, you can't look at your notes.
You have to find the mean.
Find the mean. Very good. Okay. So we're going to find the mean for both of these, and you're all going to learn how to do this with your calculator, correct?
Yes.
Okay. So we've got a mean of 35 and 28. What's the second step, Easton?
Did you find the standard deviation?
Standard deviation. Now, by the way, I'm sure that you can standard deviation, and we're always going to assume these are samples. If you do the population standard deviation, you will get this wrong, okay? This is always a sample standard deviation. So we've got a standard deviation of 19 and 6, okay? The third step is what, Janie?
Wasn't it you find the standard scores?
So we need to find the standard scores for the X and the standard scores for the Y. So well done. Can you tell me what I should type in order to do this?
So is it it's X minus the mean over sigma?
Okay, so these need to be in parentheses, right?
Yeah.
So the first one I'm going to click on is what? What's the X in this case?
Would it be the 21
The 21. I'm going to subtract.
from the 34? Oh no, from the mean. So the mean was 35.5.
35 and a half. Okay. I'm going to close my parentheses and then I'm going to divide by.
The 28.6.
Nope.
Or no, 19.9.
19.89. Okay. Now, let me just mention here the biggest mistake. We're going to do it the right way. Or should we do it the wrong way? The biggest mistake is people don't use parentheses when they're doing this. Okay. We're going to do it the right way, and then I'm going to show you the wrong way, and then I want you to, at the end, we'll show you how to do this wrong, and then hopefully you'll know why you did it wrong. But anyway, we'll do it right. Okay. So since that was Janie that did that. Seth, can you tell me how to do it for the Y variable? Did Seth leave? I think Seth might have left. Wes, can you show us how? Or tell us how?
Yep, you'll do the exact same thing. You'll do your in parentheses. You'll do your B2 minus
which is the 34. Okay, minus.
Yep. Minus, and you'll need to do your little nifty $sign trick. But it'd be B14.
Yeah, so I can tell you are an Excel guru. You're noticing that. Okay, good job. Divided by.
And divide that by your sigma, which is 6.31.
6.31. Okay. And of course, we're going to repeat that, which is really easy to do with Excel, a bunch of times. Okay, so now we're back to Ali again. What do we do next? Based on this formula.
Oh, sorry, I was on mute. So you add you find the sum of all of them?
Oh, you missed a step.
Oh, darn it. I don't know what the next step is then.
Okay, so you're looking here. So we found a z-score here. We found a z-score here.
Oh,
what do
so
we
you
do with these two
multiply them?
z-scores? We need
You
to multiply.
Okay.
So we need to multiply them. So what am I multiplying together?
So you're multiplying the C2 and the D2.
Yeah, so the negative 0.73 times the positive 0.849. Okay. And we're going to do that a bunch of times. Okay.
And then you find the sum for all of them.
And you find the sum.
Okay.
So now you're greedy and you did 2 steps. That's good. All right, so we'll find our sum. Okay. And then who's next? Easton, you must be next because Bridger's not answering. What do we do next?
So then you divide that by n-1. So you do divide it by 11.
Yep, we've got, let me make sure how many we've got here. Got 11, so we're going to divide by 10, right? Does that make sense?
Yeah.
Okay. All right, so now your calculator probably can, if you're using Excel, you can find the correlation coefficient. You would use the X variable and you would put a comma for the Y variable, and you can check your answer, which is exactly 0.174. So you can now show that you're as smart as a computer. And I'm certain that if you typed in correlation coefficient on your calculator and into YouTube, they would show you how to do this. But the fact of the matter is, I need to see all of these steps on your test, okay? If you want to check it and you want to make sure you have the right answer. Now, as I mentioned earlier, the most common mistake is to forget to do the parentheses. So what I'm going to do here is I'm going to erase the parentheses for a minute, okay? So in this case, I'm going to copy this formula down, okay? So now, the problem is, so the only mistake that we've made here is that I haven't used parentheses. So I've got a value, my correlation coefficient is 916.867. Now, can you all recognize immediately why that is wrong? Why is 916 a wrong answer?
It's over 1.
It's greater than 1, okay? So hopefully if you get something like that, now let's back up here. I'm gonna go back here, okay? Now you should see that these numbers are, the biggest number we've got is a 3 here, and then a lot of these are close to 0, okay? And in fact, these numbers are 0 to 2, it looks like, pretty much positive, negative 2, okay? So, so that's why it's very important to make sure you're doing these. So, so let me back up again. So if you, let's say you forgot to do your parentheses again. Whoops. Okay. Even if you forget your parentheses, I will give you more points on your test, even if you give me the answer of 916.867, than I will if you just give me this correlation coefficient and don't show your work. You'll get 0 points for not showing your work. Does that make sense? Okay. All right. So, but hopefully you remember your parentheses. So that's probably the most common mistake. Another mistake is to skip a step. But this will definitely be a test question. I don't know that I made you do any of this on the homework, but I will make you do this on the test. So, and you can have that formula. You'll just need to memorize those steps if you like to memorize things. So, all right. So do you guys get any questions for me? Do you feel comfortable drawing the scatter plot by hand? Because I'm not going to make you do it in Excel. Could you draw that by hand if you needed to?
Yes.
I saw Easton shake his head. Okay. All right. So any questions for me? All right. Well, I know we're out of time. So, oh, actually, one more question for you. So if my correlation coefficient is 0.174, and you didn't look at your scatter plot, you would say what?
It's weak correlation.
Weak positive, right?
Mm-hmm.
Weak positive correlation. Okay. But I think based on the scatter plot, I would probably say weak and nonlinear, because it does look a little bit curvy on this. There's a definite curve there. So that's what I would say on this one. Okay. All right. So quiz will be due on Monday. Homework's due on Monday. I think I've already posted it. And I will post my notes. If you have a minute and a half to watch that Freakonomics video, I think it's really interesting. Although I've basically told you, I gave you a big spoiler on it. So anyway, I will let you go. So thanks everybody for coming, and we will see you all on Monday.
Thank you.
Thanks.
Yeah, we'll see you.